positive y-axis, the negative y, or the positive z-axis, or the negative z-axis direction. Got an answer? Okay.
Whoa.
First right hand rule. Pretend to grab the wire with your right hand with the thumb in the direction of the current. Whoopsie, my thumb's not in the direction of the current because my thumb's going like, whoop, gotta grab this way, yes? Okay. Your fingers curl in the direction of the magnetic field. Yes? So basically, the magnetic field is going to be going around back, round front, this way. You making fun of my hand?
No, my hand.
Oh, your hand, okay. So basically, it looks like a donut shape around the wire. And at that top point right up here, which is comparable to point P right there, the direction is out of the page. And in terms of the XYZ axis, what direction would that be? Farrell? I think we said that out of the page is positive Z. Yeah.
No, it's now negative.
Yeah, it's negative.
Unless you told us wrong yesterday.
Hold on.
My life is a lie.
All right, let's clarify that. I might have told you incorrectly yesterday. Let's make sure we have this right here. So basically, you have your positive X and your positive Y. And basically, if you curl your fingers from X to Y, like this, of your right hand, then your thumb points out of the page, yes? And the Z-axis in the positive direction would be coming out of the page this way. Out of the page, towards us. Okay. So it's like a three-dimensional picture. Positive X to the right, positive Y straight up. Positive Z would be coming straight out of the page. Another way of notating it, sometimes it's shown like this in physics. X-axis, Y-axis, and where there's the origin there, sometimes just a big circle is there, kind of indicating that basically the Z-axis is out of the page. Because in physics, a circle is denoted as out of the page, and an X is a indication of into the page. So with that notation going back, at point P, it's definitely out of the page. We all agreed upon that, and that would be considered the positive Z direction. Sorry if there was any confusion from yesterday's notes, but this is correct. Sure. You know, like this picture here, it shows going, this isn't down though, this is supposed to be like, coming out of the board, okay? All right. Now, if a magnetic compass was placed at that point P, and you held it in your hand, you know, here's your hand. You held it flat in your hand, right above the wire. The little compass needle would swivel around and come to a stop. And in which direction would the little baby compass needle be pointing? Out of the page. Because basically, ladies and gentlemen, whatever the direction of the magnetic field, that's the direction that a magnetic compass points when placed in the field. That's how the magnetic field got its direction identified in the first place. So a magnetic compass always points in the direction of the magnetic field when placed in the field. So in this case, the magnetic compass isn't necessarily pointing towards the geographic North Pole, because the wire's magnetic field is way stronger and has way more influence. So the Earth's magnetic field takes a way back seat. And some people are like, oh, I thought the magnetic compass always points north. Oh, that's only when it's way far away from all other magnetic fields. And it only is experiencing the Earth's magnetic field. If it's experiencing the wire's magnetic field, whoopsie, take that back. Then it would be coming out of the page. Questions, comments? We good with that? Shira?
Wait, so if you had a compass and it's pointing in the direction, how do you know that if it's pointing north or if it's being influenced by a wire in the vicinity?
Well, that's a good question. And sometimes, like in the classroom, that even happens. You know, it won't even be pointing north, and you think it's pointing north, but there could be a wire in the wall. Usually, if you're in the woods and you're far away from all devices, then you're pretty confident that there's no other magnetic fields around. But inside of a building, you have to be careful. Good question. All right, so that leads to today's question. How can a magnet be made that can be easily turned on and off? We know we could pick up things with permanent bar magnets. We could bring it over and pick up paper clips. But it's not very easy to make a permanent bar magnet unmagnetized, although that can be done too. Eventually we'll learn. And of course, since we saw that a wire with an electric current in it has a magnetic field, yes? Well, we're going to make use of that fact, because if you go back to that wire and you turn the electricity off, say like right here, turn the current off, then what's immediately going to happen to the magnetic field around that wire? Yeah, it's just going to immediately disappear. And the compass needle would go back to pointing towards the geographic North Pole. So we're going to make use of the fact that we could turn this magnetic field on and off as easy as turning the current on and off. Okay, so let's get started with this. Let's say we take the wire and we make it into a loop. Typical question would be, at the given points A, B, C, and D, what are the directions of the invisible magnetic field due to the loop of wire? And you'd have to be told the current direction. So let's say that the current is going in this way, going up through the wire this way, down this side, and out over here. And at points A, B, C, and D, we want to identify the direction of the invisible magnetic field around that current carrying conductor due to the current carrying conductor. Well, what you have to do is just apply that right-hand rule, even though the wire is curved. If you just look at a little tiny section, say like right through here, like that, yes? And you apply the right-hand rule, by grabbing the wire with your right hand, whoopsie. At that point C, what is the field going to be doing? Going into the page. And to denote that, you could simply just put an X there, because X denotes into page. And if you curl your fingers all the way around over to the other side, what is it going to be doing over there? Out of the page. And we can put an O, and the O denotes out of page. And you guys can do the same thing to the other side. Determine the direction of the magnetic field at point A, and determine the direction of the magnetic field at point B. But careful, because over there, that same current happens to be going up in the wire. So what do you think, George, at that point B? Okay. If you grab the wire with your right hand, thumb's going in the direction of the current, yes? Right. Your fingers are going in the direction of the magnetic field, yes? At that point B, are my fingers going into the page or out of the page? Into the page. See how my fingertips are pointing into the page? And then if I wrap them around the back of the wire over here on the left-hand side, like let the pen now be the wire, yes? If I wrap them around over here, then on the other side where A is, what would my fingers be doing? Out of the page. Do you see it now? So then what can I put there at letter B to denote into the page? Yeah. And we could put an O at point A, indicating out of the page. And as a matter of fact, we could play this game at any point around that loop of wire, and it turns out that the magnetic field lines are always going into the page, inside the loop, and coming out like that, outside the loop. In, out. In, out. So inside that loop of wire, you get a relatively strong magnetic field because you get many field lines going the same direction. And of course, if you happen to go and turn the current off, that magnetic field would disappear. And if you turn the current back on, the magnetic field nearly instantly reappears. Now, this field is definitely stronger than the field around a single straight wire, but yet it's still not strong enough to pick up much of anything. But if we take this single loop of wire and we loop it multiple times into a coil of wire, what happens is this magnetic field here on the inside gets strengthened over and over again. So I'm going to take this loop of wire and re-loop it and make it into a coil. Now, it's helpful to imagine like a roll of paper towels that just ran out of paper towels, and you have that cardboard inside holder, yes? So it's helpful if you draw that first. Whoa. we're just going to use that as something to wrap the wire around, to loop the wire around. And then when I loop the wire now, I can make it kind of look three-dimensional by not showing the wire when I go around the back side. So let's say I bring the wire up over here, yes, and then I bring the wire up around top and then around underneath. I like it because it kind of looks like an S for Sosinski. And then I make another S a little bit over here. And then I make another S. And it kind of gives the three-dimensional look that I'm looping the wire around that little inside holder. And then the last time, I just bring the wire down. And let's say I connect it to a switch. And then a, whatchamacallit, battery. Well, when I close that switch and connect these two pieces of wire, I get an electrical current going through the closed loop. Yes? And if we're following conventional current, the longer wire here is the positive, the longer little line here is the negative. So we know the fictitious positive charge that flows through the wire would be going up this way, and I'll draw that in red. Yes? And going through the loop-de-loop, down the other side, back to the battery. And just like we saw in the single loop, how all of the magnetic field lines on the inside were going the same way, similarly with multiple loops, all of the field lines on the inside, don't even draw this, but inside that cone there, they're all going to be going the same way. Which way? I'm not sure quite yet. We're going to learn how to figure that out. But here's the cool thing. When you look at the resultant field of all these loops of wires, the overall shape of the invisible magnetic field looks exactly like the magnetic field around a bar magnet. Oh my God, who knew? Remember how the magnetic field around a bar magnet had magnetic field lines come out one side and then loop in, come around like this, loop in. The magnetic field looks just like the field around a bar magnet. Let's just take a moment to review what that field looks like. I'll come right back to that in a second. And you might not even want to copy this down because you already have this in your notes. But if we had a bar magnet like this, and this was the North Pole and this was the South Pole, remember the magnetic field lines loop out around the north and into the south, out around the north, into the south, like this? You see that general overall shape? How it's very, very similar to the invisible magnetic field around a current-carrying coil of wire. The only difference is, if you have a permanent bar magnet, That magnetic field is there to stay. But if you have a current carrying coil of wire, what can you immediately do with that magnetic field? Turn it off just by opening up the switch. As soon as you open up that switch right there, the magnetic field collapses. You close the switch, whoop, whoop, you have the magnetic field. Arsena? That's exactly what we need to identify. How do we know the direction of the magnetic field? Of course, we could apply the first right-hand rule to any individual segment of the coil and figure it out that way. Of course, if we actually had this set up, what could we actually place inside the little, coil thing? A little free to swivel magnet, a little compass, yes? The compass needle would tell us which way it points. Or we can use right-hand rule number 2. Ooh, yes? Right-hand rule number 2 helps us to identify the direction of the invisible magnetic field around a current-carrying coil of wire. Let's write it down and then go back and apply it to this coil over here. Okay. Right-hand rule number 2, used to identify the direction of the magnetic field around a current-carrying coil. Job 1. Identify the direction of the current in each little loop of the wire in the part of the loop that you could see facing you. Identify direction of currents in the loops of wire on the side of the coil facing you. That's going to be job 1.
Can't you draw it either way with the coil facing?
We're going to go back and look at this. Okay. Identify the direction of the currents in the loops of wire on the side of the coil facing you. So let me go back. Now, sometimes the current direction isn't even given at all, and you have to start off by looking at the battery. Yes? And look for the positive terminal and know that the current leaves the positive terminal like this, yes? Then you follow the current going up the wire, yes? And notice, when the current first hits the coil right here, and it goes behind the coil, is it going to be going up or down? It's going to be going up. And then in front of you, the side that's facing you, what is it going to be doing right here? So right there, it's going to be going down. And then as it goes around back, again, it's going to be going up. And then as it comes around the side facing you, it's going to be going down, and then up, and then down, and then up, and then down, like that. So basically, we identified the little tiny baby currents in each little strand of the loop. On the side that we're viewing, those currents are going down. So those are little current directions. A lot of times, you're not even going to draw that. You're just going to get that straight in your mind. You know, which way are those little currents going in the side of the loop? Yes? Okay. Now, do you know how there's two different ways of looking at your fingernails? You can look at your fingernails like this. Of your right hand, you say, oh, here's my 1, 2, 3, 4. You know, here's your thumb, and then, oh, look at my nails, and you look at your nails, you know, like this way, yes? Or you could flip your hand around and bend your fingers, and you can look at your fingers like 1, 2, 3, 4, hopefully.
Looks like a cactus working a muscle.
You can look at your fingernails this way, yes? Oh, no, that's not, no. This here is the thumb.
It does.
Okay. It's not a nose of a guy with a bad haircut.
You sell that to
Okay.
like box.
Okay. Well, what you're going to do is you're going to look at your fingernails either this way or that way, and you want to end up putting your fingernails, or your fingertips, if you will, in the direction of the little currents that you just identified in step 1. So, job 2 here.
I look at this. I've never seen any of my fingernails. Never. I haven't been here in other place. I've never seen any of them. It's an app.
I can do it for 30 seconds probably.
So position your right hand to view your fingernails in such a way that your fingernails are pointing in the direction of the identified currents that you did in step 1. Position your right hand to view your fingernails in such a way that your fingernails are pointing in the direction of the identified currents. Yes? So let's go back and do that. So basically, in this case, I'm going to have to view my fingernails like this, you know. And here's my thumb, and my fingers are going to come around 1, 2, 3, 4, you know, like this, you know. My fingernails are going to have to be positioned like this because the currents are going down. And my fingernails have to be pointing down. Yes? Hold your thoughts here. Let me just. Okay. When you position your fingernails in the direction of those currents, the thumb points in the direction of the magnetic field lines inside the coil. The thumb points in the direction of the magnetic field lines inside the coil, or towards the north pole of the coil's magnetic field. This would be the south pole. So when you position your hand, and you see how your thumb here would be pointing to the right? Well, two things. Your thumb tells you that inside the field lines are going to the right. And if the field lines are going to the right, yes, and they're coming out this side over here, think back to the bar magnet's magnetic field. Where is that sucker? In the back? Oh, there it is. You see the side where the field lines come out? That's the North Pole side, yes? You see the side where they come out? That's the North Pole side? Well, same thing here now with the coil. The side where the magnetic field lines are coming out, that's the North Pole of the coil, and that's the South Pole. So you point your fingernails in the direction of the little identified currents in each strand, yes? And your thumb points in the direction of the invisible magnetic field lines inside the coil, which happens to be towards the magnetic field's North Pole. Let me just write that up. So now let's go forward here and let's have you try one. Which pole of the coil's magnetic field is on top? It turns out that if you close this switch right here, if you close that switch right there, okay, we identify the current directions. Here's your positive, here's your negative. So the current's going to be going this way. This time it's going to be going this way, and then around back. Current this way, then around back. Current this way, then around back. Current this way. Yes? And then you could either look at your fingertips this way Or you can look at your fingertips and, of course, curl them towards you. Oh, I need to put a thumb here. And which of these two are your fingertips for your right hand going to be pointing with these little baby currents? And the answer, of course, is this one over here. So then your thumb pointing down tells you that the invisible magnetic field inside the coil, that makes the same loop like the field around a bar magnet. Well, the thumb tells you that those invisible magnetic field lines inside the coil are going down. And if they're going down inside the coil, as the thumb tells you, they'll be coming out of the bottom of the coil and then wrapping around the outside and then going back down in over here. And if you compare this with a bar magnet's magnetic field, the end where the field lines come out, that is a north pole, and the end where the field lines go in, that is a south pole. Now, this one here looks identical, but if you look closely, the currents, even though the battery is positioned the same way, the current, even though it's going this way, going in just like before, this is the positive, but now look at the wrapping. Now it's going around back, and then it's going around front, around back, and then around front, around back, and then around front, around back, and then around front. And this time, if you put your fingernails, you'd have to put them like this, and basically the thumb tells you that the field lines are going up on the inside of the coil, looping around. Therefore, up top here would be a north pole.